Hey folks, Todd Coburn here with your Aerospace Structures series. This video is a supplementary lecture to give a review of some basic matrix operations that are going to be needed for our composites and finite elements classes. Let's take a look at how this works. So just to review some basic operations, a matrix is just a rectangular array of elements. So we're used to dealing with scalars like a 1 or a 5 or a 9 or a variable like an A or a B or a sigma. Now we're going to be dealing with a whole bunch of those, and we're going to put them in an array, a n by m array, so where the first subscript is the row and the second subscript is the column. So an A matrix can consist of a bunch of entries of A11 in the first row, first column, A12 in the second column, A13, and so on. And then the next row will be A21, A22, and so on, just like we see here. So this particular row has m rows and columns. Once again, the first subscript is the row number and the second subscript is the column number. It's common to show this that can be called a matrix. It can be called a vector, although usually we use a vector for like a column matrix or a row matrix of a single row or a single column, and usually we use the term matrix for when we have more than a single dimension on that matrix. So an m by n matrix. A row matrix then would be a 1, n matrix, and a column matrix would be a m, 1 matrix because it only has one column. Okay, so it's called rectangular if the number of rows and columns are the same. And well, actually, let me restate that. It is a rectangular matrix because it has so many rows, so many columns. No matter what the size is, it's always rectangular. But if those two subscripts are equal, then it's if the number of rows equals the number of columns, then it's called a square matrix, obviously. So we can call that, we can identify each entry in the matrix by its position, ij, where I is the row number, j is the column number. This is standard nomenclature. A row matrix then is a single row. We'd call it a 1n matrix. It would look like this. A column matrix looks like this then. Now we have however many entries, 1 through however many, but there's only one column. A lot of times if we're dealing with a column matrix, we will use braces instead of brackets to deal with it, and often it's common to use just parentheses when you have a single row matrix. Okay, we can also show a column matrix as a transpose of a row matrix. This actually is a quick way to implement for some kind of programs to put in your matrix. Instead of putting each entry, each row entry, you can put in each column entry and then take the transpose. Okay, the transpose of the matrix then is caused by just flipping the two indices. So if you have a matrix like this A matrix, 1, 1, 1, 2, 1, 3, and then going down 1, 1, 2, 1, 3, 1, what that does is just reverse that. It flips that matrix. So now the first column is in the first row, and the first row is in the first column, and so on. So we see that just flipped. Therefore, A1, A2, A3, the transpose of that, if we didn't have that little T symbol, that would just be a row matrix, but that transpose means we're going to take that row matrix and flip it, and that makes it a column matrix. In the same way, the transpose of a column matrix makes it a row matrix, as you can see here. Got it? Okay, so these two matrices are equal if they have the same number of rows, same number of columns, every single entry is the same. That's obvious, so to speak. A diagonal matrix is a square matrix where all the main diagonal has some value, but all the other entries are 0. These are commonly used and encountered in engineering applications. If all elements on the diagonal happen to be the same, it's called a scalar matrix because it has the exact same effect of multiplying a matrix of values by just a scalar hitting every single element. And when you have a diagonal matrix of a constant, then it has the same effect as just multiplying that matrix by a scalar. If all elements are 1 on that diagonal, that's called the identity matrix. Has the same effect as multiplying a number by 1. It just returns the same thing as you can see here. A lot of times we'll call it the I matrix for the identity matrix. The determinant can be computed this way. Okay. We can add the matrices. To add two matrices, they have to have the same number of rows and columns. If they don't have the same number of rows and columns, they can't be added. If they do have the same number of rows and columns, you just take each entry and add it to the corresponding entry in the other matrix, as you can see here. And that means that the order doesn't matter. It's commutative and associative, as you see in there. So we can subtract the same way. Once again, we need to have a square. We have to have a matrix with the same number of entries. Rows and columns need to be the same between the matrices. And basically what you do is you take the first matrix and you subtract the exact same element from the other matrix for each and every element, and that creates the subtraction. So for multiplication, what we're going to do, let's look at a couple cases. First, let's look at a case where we're multiplying a matrix by a scalar. So if we have a scalar S, or maybe it's 5, multiplied times a matrix, this A11, A2, A12 matrix. Let me just augment this. If we have this operation where we have a scalar, some number S, multiplied by this matrix shown here, basically all that involves is multiplying each and every element of the matrix times the scalar, as you can see here. Now, if we have the product of two matrices, you can show it in tensor notation like this, where the multiplication of A times B is going to be A. If A has IK and B has KI, then that would define the multiplication. Now, you'll notice the inner dimensions. You'll notice A has 2 elements and B has 2 elements, and the ones that are in the indice that is closest to each other, the second indice of the first matrix and the first indice of the second matrix, have to be the same for the multiplication to exist. For example, if we're going to multiply, let's say we're going to multiply this A matrix times this B matrix here. What we're going to do is we're going to multiply each row times each column, and that's going to give us 1 element. And the way that works is we're going to have, let's switch this to here, A11 times B11 plus A12 times B21 plus A13 times B31. That's what we see here. And when you add those all together, those multiplications, you get this 1 element. Now, we do that again, which means we're going to take the second row times the column, which is going to give us that next term in our column matrix. So we're going to have A21 times B11 plus A22 times B21 plus A23 times B31, and when you add that all together, you're going to get this second one. Then we do it a third time, where we're going to have this row times this column. So once again, the matrix multiplication is going to be row times column gives us the first element. Row times column gives us the second element. Row times column gives us the third element. Now, if this B matrix had consisted of 2 columns, we would go through that whole process again, multiplying the first row times the second column second row times the second column, and third row times the second column, and that would give us the 3 entries in the second column of the solution. This particular matrix only has one column, therefore it only ends up with a single column matrix. That's how this works. Inverting a matrix can be a bit of a challenge. Here's a definition of that, and what we're going to do, and actually for all these operations, is I highly recommend that each of you have a strong engineering calculator that handles matrix methods. This will make all of these operations easy. You need to understand how to do these operations so that your computer doesn't lead you into, your calculator doesn't lead you into mistakes. But we're going to use our calculator so that we can learn higher things than just doing matrix operations, which we should have learned some time ago. So I'm not even going to cover computing the inverse of a matrix. I'm going to encourage you to have a calculator that will do that for you. It will be very challenging to pass the class without that. And then solving linear systems of equations. We also learned how to solve systems of equations in linear algebra, and you should be able to do that. But we're not teaching that in this class. We're going to use our calculators to do that heavy lifting. You need to understand how to multiply matrices and how to set up the inverse and let your calculator do the inverse. So this is true right here. If we have a system of equations, y equals a times x, where y and x are both column matrices, and a is a matrix, rectangular matrix, then we can write that by saying the inverse of a times y is equal to x, and then let our calculator solve that problem for us. Okay? So let's take a look at some of these concepts. Let's say we have a set of equations like this. This is one equation we're going to run into quite a bit in this class. We're getting stresses from strains with some matrix of constants. We can see we have 3 rows and 3 columns in the main matrix here, in the stiffness matrix. We have, this matrix here has 3 rows and 3 columns. We're going to get 3 stresses out of this multiplication. What we're going to do is multiply this first row times this column of strains, and that will give us the first stress value. This row times this set of strains gives us the second entry, and the shear stress is just going to be the third row times that column. That's how we do this. Okay? Let's take a look at this matrix. Let's find C13. Well, if we're looking for C13, that would be the first row, third entry. That's this guy right here. C32 would be the third row, second entry. That's right there. And C55 will be the 1, 2, 3, 4, 5th row. 1, 2, 3, 4, 5th entry. That's right there. Got it? That's how we do this. Let's try this guy. Now, we can, if we are looking for these values, we can spot this. Once you understand matrix operations, we can see T31 is going to be obtained by multiplying this row times this column. Since everything is 0 except for this entry, that means it's just going to be 3 times 0.001. Tau 1, 2 is going to be from getting this row times this column, and that means since all these are 0, that's going to mean 0 times this plus 0 times this, which means all these get zeroed except for 2 times 0.001. Now this third entry, we're going to need to multiply this row times this column. That's going to be a little more involved. And what we would do is we would have to take the 5 times 0.002 plus the 6 times 0.002 plus the 3 times 0.004. Everything else is getting multiplied by 0, and that will give us the magnitude of sigma 1, like this. Got that? Once again, I'm going to encourage you to do this with TI Inspire. Let's see, the easiest way to do this will be to use your calculator. So if you have a TI Inspire or equivalent, you will turn that puppy on, and what you'll do is you'll populate each matrix in your calculator. Now in this class, there's a wide number of calculators out there that will do this. This is my old HP that I've been using for a number of years. I recently got the TI Inspire since I found out a bunch of my students have that. That seems to be one of the leading ones, so I can try and help provide tools for that. If you have this calculator, I'm going to show you how this is done. If you have a different calculator, it will be done in a similar fashion. You just need to make sure it has all the capability that I'm going to show you here. The easiest way to solve this, now in this case, remember the tau 2, 3, 3, 1, and 1, 2 were easy to determine by hand because each of those rows is all zeros except for one entry. That makes that quite easy to calculate. But for any other calculation, even the stresses that we calculated in the last time, even though that's not a very tough calculation, it's a lot faster and less prone to error if you learn to use your calculator swiftly. So you can put this matrix in your calculator. Here's how we might do that with the TI Inspire. First, you're going to create the matrix. Now, the TI Inspire has a matrix function. You can go in, open a matrix, tell it how big it's going to be, and put in every entry. The problem is that takes time. I have found it's quicker to just type in your matrix. You do that by using square braces. You're going to use a comma between each column entry and a semicolon between each row entry. Let's see how that works. I found this can be done pretty quickly if you practice this. So in this case, our first row is 5, 6, 3, 0, 0, 0, 0. So what we're going to do is we're going to hit our TI Inspire. You're going to hit the, actually you've got to hit Control and parenthesis in order to get that square bracket. And then you're going to put 5, the comma is right down here on the lower left, 6, 3, 0, 0, 0. That ends the first row. We now want to tell the calculator that we're going to the second row, so we use a semicolon. To do that, you're going to hit this little button down here which starts with a question mark, 3 up from the lower right, and you're going to navigate over to the semicolon, which is in the second row, third column. Hit enter. That puts that semicolon there, and you're going to put the next row, 2, 3, 4, 0, 0, 0. Semicolon. Next row, 6, 9, 8, 0, 0, 0. Next row, so you hit the semicolon again. 0, 0, 0, 5, 0, 0. Next row, 0, 0, 0, 0, 3, 0. Next row, 0, 0, 0, 0, 0, 2. Enter. And that's going to dump that matrix into your calculator screen. You then want to store the matrix. You do this by hitting the little store function, but that's buried underneath the variable functions. You're going to hit Control Variable, which actually just means store, and then you're going to give it a name. Let's give it the name A. So you plug in an A and hit enter. Now your calculator has stored that matrix in the variable name A. That all those elements. Okay? Now we're going to need the other thing. We're going to be multiplying this A matrix by what we're going to call the B matrix, and that happens to be a column matrix. Now the problem with making column matrices is you're going to open the matrix with a open bracket, and then you're going to have to navigate over the semicolon, which is not easy to grab on the TI Inspire. It's much quicker to grab the comma because that's right down here. It's a direct key. So I recommend the easiest way to do this is to make a row matrix and then transpose that puppy. So we can make that row matrix by putting in every entry as if it were a row, 0.002. So we're going to open the parenthesis, or open our bracket, Control parenthesis gives us a square bracket opening, 0.002, comma, 0.0002, comma, 0.004, comma, 0.003, comma, 0.001, comma, 0.0001. Close square bracket. And then we're going to make the transpose, which means you're going to find the at key, which means you've got to go Control, and underneath the Bible key, you will find Control Bible key actually gives you an alphanumeric keyboard, and right in the middle of that, in the third row, sixth column, you'll find the at key. Put that in there, and then you're going to need a capital T, so you're going to hit Shift T, Enter, and that will enter this as a column matrix, and then you're going to look at it in your calculator. That'll drop that column to the screen. You're going to look at that and make sure every entry is correct, as you should have checked out each entry of your matrix, your A matrix, when you put those in. Then we can we're going to store that. We're going to store that in B. So we're going to hit Store and then give the variable name B, which means we're hitting Control Variable. That's the store. And then whatever name we want to use, I'm going to call it B. We now are ready to multiply this out. So now all we have to do is put in A, multiply button, B, enter, and that will drop the result, which will give us, now it's only going to give us the column matrix. We're going to need to recognize that those are the elements of the matrix we just calculated, which means sigma 1 is 0.20232, as we found last slide. Sigma 2 is 0.0206, and so on. Got it? Let's look at just a couple other things. All right, let's now say, okay, let's say instead we have the same A matrix, but now we know the stresses, we don't know the strains. Now we have to solve a system of equations, or we have to compute the inverse, but we can do that with our TI Inspire as well. So what we're going to do is we're first going to enter that A matrix the same way we did before. Now in our case we already entered it, so we don't need to do it again, but if we were entering it the first time, that's what we would do. Store that puppy. Enter the other column matrix in the same manner we did before, but putting in the values of this matrix, no problem. And we're going to store that. I'm going to call it C. And then we can do this operation. Oh, it looks like there's a typo here. This should not be an uppercase. We stored that as a lowercase a. It looks like my computer changed that to uppercase. That's a lowercase a. So we're going to hit lowercase a, whatever we stored that variable name as. We're going to hit the up arrow key, which means we're raising the power. Minus key 1, which raises the -1 power, and then we're going to hit the right button so that we get out of that uppercase down to the lower line, times C, which is what we named the other matrix. We're just multiplying the inverse of the matrix, and this is this A upper caret -1 gives us the inverse, multiplying that by our other matrix, which we call C, and that will solve the problem. We'll get rid of this writing on the screen, and get rid of the writing on the screen, and turn off the pen, and that gives us the answer. Now once again, the calculator is just going to throw that column vector on the screen, but we know the first entry is epsilon 1, and so on. That's how it works. Let's look at one more operation. Let's say we want to create a new rooters matrix. We'll learn about the rooters matrix later, why we're messing with this matrix. Now we could enter this in the same way we did before by entering 1, 0, 0, next row 0, 1, 0, next row 0, 0, 2. But we can do this even quicker by using the identity function, by augmenting this matrix, starting this matrix as one matrix and tweaking it into the matrix we want. Let's take a look at that. We can use this function if we just type in, now actually I show it as uppercase, but that actually should be a lowercase I. Identity, open parenthesis 3, close parenthesis, enter, is going to make a 3, it's going to give us an identity matrix, a 3 by 3 identity matrix. So it's going to give us almost the rooters matrix, except the lower right entry will be 1. We then just need to change that last entry. So once we've done this, we're going to see our calculator is going to drop a 100, 010, 001. It drops an identity matrix, a 3x3 identity matrix. Let's store it, and we'll call it R, which means we're going to store R, which is control variable R. Enter. Now we've stored that matrix, which isn't quite correct, and now we just need to tweak the matrix. We can do this by first putting in the value. We need to change this last value to a 2, and then we can store this. Oh, and I got another typo here. This should be, we're going to store it in R. We're going to do the store, but there should be a right parenthesis right here. This should be lowercase I, not an uppercase I. So we're going to have R, 3, comma, 3, and then enter. And that will store that in that last spot. It will replace whatever is there with that number that we had or storing there, and that will have the effect. And your calculator will throw this 100,010,002 Reuters matrix. Sound good? So I'm going to have to go work on my dog who's going crazy. Must have an Amazon package arrive. That's how you do it. Rewatch this video as much as you need. Pull up your linear algebra book. Get yourself a good calculator. You need to practice these operations until they're second nature. Entering matrices, operating on matrices, you can do those, you can practice adding and subtracting matrices. My homework will have some practice problems for you. Solving systems of equations where you're just multiplying matrices or taking the inverse and solving the system equation. You need to be a master of those because you want to be able to focus on the other principles that I'm going to be teaching you that you're going to be learning in this class. Enjoy.